Alright, welcome back. In the last video we were talking about the capstan problem and the strategy of considering differentials, and I'm showing a problem here that relates to that strategy so that we get some sort of feel for how it works. And here we have bacterial colonies growing over time, and we're trying to find an expression for the change in the amount of bacteria in a time delta t. So that change in population delta p is going to equal first k, which is our constant for the division, and since that k is expressed per cell, we need to multiply that k by the amount of bacteria we have at the beginning of the time that we're considering. So we'll multiply that by p of t. So now what we have is the number of cell divisions per cell times how many cells we have. So that leaves us with a quantity that's the number of cell divisions we have in a unit of time. So to get the number of cell divisions total, we need to multiply that by some time delta t. So that's all well and good. And if you look at this quantity on the right side with some dimensional analysis, looking at units basically, since k is expressed in divisions per cell per time, its units will be cells, well, divisions over cells times time. And we're multiplying that by a number of cells, which cancels that expression in the denominator, and by an amount of time, which cancels the other one. So we're left with just a number of cells, or divisions, I should say, on the right, and a number of divisions or additional cells on the left. So the units work out. But now we can use this, scrolling down a little bit, if we divide both sides by this delta t, we now have this expression. And now if we take the limit as delta t becomes very small, making delta t an infinitesimal time step, we get this derivative now, dp dt equals k times p, or p of t. And now if you're familiar with a differential equation like this from single variable calculus, this is something you can solve using separation of variables, which means that we try to get all of the p's on one side and everything with the t on the other side. So in this case we divide both sides by p of t and multiply both sides by dt. So we end up with is dp over p, no longer writing the of t. I'll just get rid of that for convenience. That equals k dt. And now we can integrate that, which, switching colors, if we integrate both sides of that, now because we have our differentials and our variables match up, on this side it doesn't matter because k is independent of t. So when we integrate that, what we're going to get is the integral of 1 over a variable is the natural log of that variable. So we get ln p over here, and the integral of k dt is just kt. And we get a constant of integration as well. And now we can solve this equation for p by simply taking e to the power of each side, exponentiating each side, you could say. So if I have a little more room to scroll down. So e to the ln p is just p, and that gives us e to the kt plus c, but we can use our exponent rules here. If we raise this to the sum of these powers, that's the same as e to the c times e to the kt. But e to the c is just another constant, so we can change this now to p equals c, or this is a different constant c from the other one, but still a regular old arbitrary constant. P equals c times e to the kt. So that's great. And if we just look back at what we did, the procedure for solving this was, given our constant here, we wanted to consider what happens to the population after a certain time step delta t. Then we took the limit as that time step becomes very small to get a derivative, or really a differential equation. And then we used the method of separation of variables to solve that differential equation for our population p. Now you may be wondering why I just spent all that time discussing a population model and what this has to do with the capstan problem. But as you'll see, this is a very similar problem, and in the analytic form of the solution, it's almost identical to the Capstan problem. So getting back, here's the Capstan diagram that became very messy in the last video that we were thinking about. But we're going to apply the same strategy here. So let's switch to red. So what we want to do is look more closely at this part here, this infinitesimally small slice of angle d theta. And I wonder if I have room. Oh, no room over there. Where do I have room to do this? Okay, so I realized I didn't have any room to draw the infinitesimal slice in the last video, so I just stopped the recording, and now I'm doing it in a new window. So, okay, so this will be our infinitesimal slice d theta, even though it looks very non-infinitesimal. We want to draw it large enough that we can see what's going on. So that's our slice d theta, and let's switch color. How about like a blue? So on either side, we have some force pulling on it. Let me draw it big so we can see what's going on. So if you remember, this side over here was closer to the load force, and this side was closer to the hold force. So the force on this side is going to be greater than the force on this side by some small amount. So I'm going to call this one F plus dF, because it's slightly greater. And this one here will just be F. So that's good. Okay, so now what we want to do is use some basic geometry here to... Hot pink again? Yeah, why not? Some basic geometry to determine these angles, because we want to decompose these forces into horizontal and vertical directions. Because our ultimate goal is to use Newton's laws to sum up the forces acting on the rope, and use that to get a good relationship. I also left out one other force here, because since this force is greater than this one, the rope wants to slide this way, but there's another force acting on it. There's the friction force, which is trying to oppose that motion. So that's like little f, we'll call that. So that's another force, and that's because that the rope has some coefficient of friction, mu, like I said before, against the cylinder, so that friction is trying to stop it from sliding. So that's good. But first, decomposing these. So we can use some basic geometry here. Now my mu's going to get in the way. But because these are radii of that cylinder, these are both the same. So by basic geometry, these three angles have to add up to 180 degrees. So let's see if I can get this right. This angle then has to be 90 minus d theta over 2. And this has to be the same, because then when we add those all up, we'll get 180 minus d theta plus d theta, which just gives us 180, so that's good. But then we also have that these angles here have to add up to 180 because they form a straight line. And this is a right angle because the force is tangent to the circle. So we have that this angle here plus this one here also has to add up to 90. So clearly this angle is d theta over 2, and so is this one. This picture is beginning to look very psychedelic. Okay, so I think I'm out of time on this video as well, but we will figure out how to use these relationships to our advantage in the next video. So I will see you there.